Hello, this is another screencast on mTree. In this particular screencast, we'll be talking about agent memory used to store internal aspects of agents across rounds. So what we're going to talk about today is a couple changes to mTree that were made necessary to support agent memory and some other features such as the web UIs. And as a result of those, it's possible that it will affect your usage. You might get some errors, and we'll explain what those are. We'll also look at the mechanisms to store data between rounds and talk what does that mean, talk about what does that mean. And we'll also talk about how to access the data that has been stored in earlier rounds. So obviously before beginning, so you need to update your installation of mTree. This is the same as before. Pull both the copy of the GitHub repo for mTree, so the mTree develop branch, and then you also want to reinstall mTree as there are some additional scripts that are now available. They'll be more useful later on, but you want to make sure you do that. You'll also actually want to you'll want to pull the newest version of mTree examples, and you'll notice that all of the MESs have changed slightly for all of the examples available, and we'll talk about what happened there. So one of the things to be mindful of, which is sort of a hidden detail, is the memory model used in the actor system. We had defaulted to a base system in Python, and what would happen is you would create items in memory, and then they would actually be accessible across actors. So you could have an actor, and you could actually reference things in the memory of another actor. This is not really what you should do for actor systems. We had it temporarily just for ease of development, and there was a setting to configure it. So we've actually moved it, so now the default setting is to have everything have process separation. So what this means is if you attempt to access certain items, you will be blocked from doing so. It probably won't affect many of you. It's just a possibility. The other thing now will be that you need to ensure that when you're sending data between actors, it has to be pickleable. So if you've been sending raw Python objects, there are some instances where you will now get an error as a result of trying to send the object because the object can't be serialized. One thing in particular you'll notice is if you've been referring to other actors, sometimes by name, what'll end up, so for example, like self.institution in some of them, or self.institution.myaddress. The key thing especially for anything involving some of the sends, if you're referring to other actors, you have to refer to their address. So it's just something to be mindful of. The way this will normally manifest as an error is in the mTree log, you'll see an exception where it'll mention something about pickling. And it'll say it can't pickle things. And so what that just indicates is it can't serialize the whole object. And so as long as you kind of strip out the pieces of the object you don't want, or just take the properties out and then put those into the payload of the message you're sending, you should be fine. And obviously we can help if there's any issues that you run into. It's not particularly challenging. It's just something to be aware of. And again, everything just has to be serializable. So if it's just raw values, raw numeric values, that's fine, but generally the sending the whole objects is problematic. And actually the way you can, if you think this is an odd change to make, there are ways in which you can send messages. For example, if in the old system, if you're still running it, what you could do is you can send a message between, say, the institution and the environment, and you could actually, like, for example, you could send a list of items, and you could send it to the institution. What would happen is it would send a reference to the memory location for that list, so the institution could actually edit the list, and then what would happen is unknown to other people is that it's actually editing the same list that the agent itself is looking at. So this is an odd piece of minutia which might have interesting effects, but it's not insurmountable to get over. It's a fairly straightforward process to convert your code. Okay, so one of the point of this screencast is to talk about agent memory. The key idea to consider here is, mTree allows us as researchers to run multiple rounds of an experiment, and then you can have anything going on inside of those rounds. One challenge, especially in some of these simulations, is that the agents reset after every round. So that can affect your experimental capabilities, especially if you're, for example, trying to run a matching protocol on agents or something like that. So what we're now allowing to take place is the agents themselves can store pieces of data that will be transferred to a new instance of an agent across rounds. So in effect, right, imagine you just sort of have an agent, you run it, then you take the brain of that agent or the memory location of the brain and then put it into a new agent. So you can do all sorts of stuff with that. We intend to add additional features for some of the matching protocols so that, for example, agents will never play agents again, stuff like that. Those will just be discussed in a future screencast. So the data we're actually going to be storing is at an individual agent level, and then again, it does get transferred to a new agent. You're not guaranteed which agent it's being transferred to, but it'll just be, because it'll take the same settings for the previous round, create a bunch of agents, and then it'll load them all with different memories. So we'll be improving it so that we can better target which memories go where. And so that will happen. There is one potential wrinkle you might encounter. If you do let us know. The agent types. So it should, the only criterion for placing memories in the new instances of agents is the types of agents. So if you have different types, it's possible that there's possible that there could be problems with that. If you do encounter any, let us know. It should be a simple fix if it does occur. We believe we've coded around it, but one never knows. The key thing here is you can store as much or as little data as you wish. So for example, you could store a history of items. You could store all of the previous states of memory. It really is up to you. So we're basically giving you a property that as long as you save data into it, it will travel along with the agent. So what's the basics of storing? The key thing, the key property of an agent that you're actually going to look at is agent underscore memory. And so that's a dictionary. And so what you're going to want to do before you access it, because the agent memory would be available even in the initial round, so you do need to check to see if it does exist and whether or not there's a key that's there. So for example, here we're checking to see if the win rate exists in the agent memory. If it does, then if it does not exist in this case, we're setting it. So imagine, and we'll show you the example code. So this would be at the end of, for example, the first auction. And so again, we have this immediate access to agent memory, so it very well could exist, but then you might not have anything in it. So you do need to check to see if it does, if the data that you're looking for exists there. And again, it's anything that can fit into a Python hash. We might be improving it later to have object wrapping, but for now, this should be sufficient. Again, as long as it's serial. The only thing to keep in mind here, just as before, is it does need to be serializable. So if you get a pickling error, that probably indicates you're trying to store a whole object that can't be serialized. So you can either keep the individual pieces of data, or you can actually write your own pickling method so that it only, for example, takes the fields you need. So they're not insurmountable problems. If you run into anything, just let us know and we can provide additional examples. So to access a memory, it's very simple. You can just go and just pull the item immediately if you're guaranteed that it's there. That's just possible. Or you can simply check to see, does the key exist? So in this case, we're just checking, does the loss rate exist in the agent memory? If it does, then what we're trying to figure out is how to affect our bid value. So the idea here is that we're using this to affect bids over time in the simple auction. So let's look at some code. Full example. So here's a full example of an agent with memory. So it's pretty straightforward, or it's very similar to the previous agents that we had. The only thing that we have, for example, is on the auction result. If you look here, we're checking to see if the win rate exists in the agent memory. If it does not, then we'll set it to 0. And then after it's been instantiated or created, then we're just going to keep adding to the win rate. And similarly, when we're making a bid, what we're actually going to look at is the bid value, or I'm sorry, the loss rate. And the idea is the more the person loses, the more we're going to add to the bid. And so the idea should be that we start to see higher and higher bids. Because if you're in the default setting that you'll see in like MES examples 1 and 2, is that they just bid the min value. So this is actually, you'll gradually see the auction prices go up. One thing to note, and like you might encounter this again in the pickling issues that we were talking about that could come about as the result of some of the changes. When you set the sender, in previous examples we had just set sender as self, which is a reference back to the object itself. Now we're being very specific and explicitly stating that it's self.myAddress. So the idea here is that there's actually the property myAddress on these actors is an actor address object, and those are pickable because those are a key component of the underlying actor system. So if you ever see issues, especially if it's on a message, that's kind of the first thing to check is if we set the sender, and did we set the sender with self or self.myAddress. So now that we've looked at agent memory, we can run this and see what happens with our log. So now that we've talked about agent memory, we can go ahead and run this and see how it works. So if we run our simulation, you'll notice that it runs there, and we can set the win rate, or record the win rate and the loss rate. Obviously the order isn't particularly important, but one of the things we can start to see if we identify the log, look at the log, is the bids, for example, start at 10, right? Because that's the min value of this particular auction. And as you can start to see, the bids being submitted all kind of start to creep up. And so that's kind of the benefit of this memory, or this is one of the ways in which you could use these memories to do things. One thing to keep in mind, if you look at the configs for the agent memory, it's not technically important, but if you go in and set the agent memory to true in your configs, then it will more automatically do it. It's actually going to record memory if you want it to or not. This will eventually be the config setting to make it distinct. So that's agent memories in a nutshell. Hopefully it was somewhat clear, and we will be getting back with some additional updates soon. Thanks.